Well, welcome back to our course on discrete mathematics, looking at discrete structures. And we've covered a lot of interesting ground so far. Rosen does a great job of getting into the backbones of the mathematics as a part of this, but what I'm trying to do in this lecture set is trying to focus on the application. So we talked about propositions and how we can be using that for proofs. We talked about the basic structures we need to become familiar with, algorithms. Then we got into number theory and cryptology. And what we're getting into in this chapter is induction and recursion. And so there's going to be a lot of mathematical underpinnings that we're going to have to play out and get familiar with before we can get into some of the applications, which would get into the utility of recursive algorithms. And so we're going to be talking about a couple different types of induction, mathematical induction, strong induction, structural induction. So that's going to be something that we're going to see. And so we're going to have to get into some mathematics to get some perspective about that. So many mathematical statements assert that a property is true for a positive integer, for a set of positive integers. Examples of such statements are things that we'll get a chance to be covering in this lecture. A major goal of this chapter and in the textbook is to provide a thorough understanding of the mathematical induction, which is used to prove results of this kind. So we're going to be able to prove and then utilize these relationships and these approaches. Proofs using mathematical induction have two parts. First, they show the statement holds for the positive integer 1. Maybe you can think of that as a base case, and when we get into recursion, that'll be something we'll get to. Second, there should be the statement that holds for a positive integer, then it must hold for the next larger integer. So mathematical induction is based on the rule of inference that we'll get into shortly. Mathematical inductions can be used to prove a tremendous variety of results. Understanding how to read and construct proofs by mathematical induction is a key goal of learning discrete mathematics. So back in chapter 2, we explicitly defined sets and functions that we describe sets by listing their elements or by giving some property that characterizes these elements. We have formula for the values of functions. There's another important way to define such objects based on mathematical induction. To define functions, some initial terms are specified and a rule is given for finding subsequent values from values already known. Sets can be defined by listing some of their elements and giving rules for constructing elements from those already known to be in the set. Such definitions, called recursive definitions, are used throughout discrete mathematics and computer science. Once we have defined a set recursively, we can use a proof method called structural induction to prove the results about this set. So that's going to be something we'll get to. So when a procedure is specified for solving a problem, this procedure must always solve the problem correctly. Just testing to see that a correct result is obtained for a set of input values does not show that the procedure always works correctly. The correctness of a procedure can be guaranteed only by proving that it always yields a correct result. The final section of the chapter, and so we're not going to be covering this in the lecture notes, but you can see Rosen for this, contains an introduction to the techniques of program verification, something that's important. So this is a formal technique to verify that procedures are correct. Program verification serves as the basis for attempts underway to prove in mechanical fashion that programs are correct. So that's going to be something that you can go ahead and look in Rosen to get some more insight into. Okay, well, let's focus first on mathematical induction. So we'll get a perspective on what it is. We'll have some examples of proofs by mathematical inductions, and I'm just going to walk through these quickly. I'm not going to go in detail for the proofs. We'll have something where we can be considering the mistaken proofs by mathematical induction. And once again, I'll go over that quickly. And then finally, there's going to be this, I think, a useful table for the guidelines for proofs of mathematical induction. So mathematical induction is an extremely important proof technique that can be used to prove assertions of this type, as we'll see in the section in this part of the lecture and the subsequent parts of the lecture that's contained in this chapter and will be built on in later chapters. Mathematical induction is used extensively to prove results about a large variety of discrete objects. For example, it is used to prove results about the complexity of algorithms, the correctness of certain types of computer programs, theorems about graphs and trees, as well as a wide range of identities and inequalities. So in this section, we'll describe how mathematical induction can be used and why it is a valid proof technique. It's extremely important to note that mathematical induction can be used only to prove results obtained in some other way. It is not a tool for discovering formula or theorems. So let's think about this. Climbing an infinite ladder. Well, we'll see this again in a little while. Suppose we have an infinite ladder, and so we can reach the first rung of the ladder. So here, if we can reach a particular rung of the ladder, we can always reach the next rung. So we're getting a basis of recursive perspective. So from 1, we can reach the first rung, then by applying 2, we can get to the second rung. Applying 2 again, we can get to the third one, and so on and so on. So this is an example that motivates the proof by mathematical induction. So here are some basic perspectives on the principle of mathematical induction. So to prove that P of n is true for all positive integers n, we complete these steps. The basic step, which shows that P of 1, so the first case is true, and then the inductive step, we show that P sub k, then we have P sub k plus 1 is true for all positive integers k. To complete the inductive step, assuming the inductive hypothesis that pk holds for an arbitrary integer k, we show that pk plus 1 is true. And so here's just a little bit more thinking about what's going on here for this latter example. So there are some important points about using mathematical induction, and so you can refer to Rosen to get into the details. So mathematical induction can be expressed as a rule of inference, and so this just gives us a perspective of what that might look like. But this is getting more mathematical, and I'm going to try in our lectures to focus more on application. In terms of the validity of mathematical induction is valid because of the well-ordering property, which states that every non-exempt subset of the set of positive integers has at least element, and here is the proof, and so all of the proofs are going to be things that you can feel free to pause the video and look over, or go to Rosen for more thoughts about that. But here is a more picturesque way of thinking about it. So how can we consider the way that mathematical induction works? Consider an infinite set of dominoes, and maybe you've actually done this, and you could label them 1, 2, 3, 4, etc. Let P of n be the proposition that the nth domino is knocked over. So if you align these correctly, they all should go down. We know that the first domino is knocked down, so that's P of 1 is true. We know that whenever the kth domino is knocked over, so somewhere in the middle, it knocks over the k plus first domino, so we can express that P sub k, then P sub k plus 1 is true for all the positive integers k. Hence, all dominoes are knocked over. So P sub n is true for all positive integers n. So that just gives us a little bit more insight into mathematical induction. So here we're going to have a couple examples that I just want to be focusing on the results. And so we can be showing that the summation of 1 to n can be expressed in this closed form expression. So big O notation, this would be big O notation of 1 rather than having to computationally going through this and having a big O notation of n. really great improvement. So these are examples of things that can be helpful. So conjecturing and proving correct a summation formula. So we're going to have a couple examples of this coming up. So a conjecture and prove the formula, correct a formula for the summation of the first n positive odd integers. And so the conjecture is that it's n squared, and we have the solution walking through this information, and we can actually validate that, yes, we can have a closed form of n squared for this summation. So once again, that's going to help with complexity and be able to count that quickly. So we can also be looking at inequalities. And so we can, for example, we can use mathematical induction to prove that n is less than 2 to the n for all positive integers n. And so this just gives us a proof/solution for that, and you can look over that. Here's another one. Use mathematical induction to prove that 2 to the n is less than n factorial. I refer you to Rosen to get some more details on this to follow the details of what they're proposing as a solution. Here's another example. Use mathematical induction to prove that n cubed minus n is divisible by 3 for every positive integer n. So this is proving divisibility results. And so I'll just leave it to you that you can look over that in more detail. Then in terms of a number of subsets of a finite set, so we'll have it on this slide and the next slide, use mathematical induction to show that if S is a finite set with n elements, where n is a non-negative integer, then S has 2 to the n subsets. So this gets into set theory a little bit more, and so we can be thinking about these assumptions and what that might lead to. So I think getting this in context later on will be helpful, but we're introducing some of this mathematical rigor for now. So maybe if some of you guys want to get into games, simple kind of games here, you can be thinking of a checkerboard. Show that every 2 to the n times 2 to the n checkerboard with one square removed can be tiled using right triominos. And so that's what we have here over this in the next slide. I'm not going to go through this, but this is just an example of how you can be using number theory and discrete mathematics in some useful ways to bound something. Okay, we have two charts here that talk about an incorrect proof, quote, of mathematical induction. And so here is the example, let P of n be the statement that every set of n lines in the plane, no two of which are parallel, meet in a common point. So here is a quote proof that P of n is true for all positive integers greater than n over 2. And basically they're saying that this does not work. And so you can go ahead and pausing the video or refer to Rosen to think about that in more detail. Okay, well, here is, for this section, what I wanted to have as a takeaway. So what are guidelines for mathematical induction proofs? One, express a statement that is to be shown in the form for all n greater than or equal to b for P of n for a fixed integer b. Write out the words basic step, then show that P of n is true, taking care that the correct value of b is used. This completes the first part of a proof. Then we write out the words inductive step, and we go through that, state and clearly identify the inductive hypothesis in the form of assume that P of k is true for an arbitrary fixed integer k is greater than or equal to b. State when what needs to be proved under the assumption that the inductive hypothesis is true. That is, write out what P of k plus 1 says. Then we improve the statement P of k plus 1, making use of the assumption P of k. Be sure that your proof is valid for all integers k with k greater than or equal to b, taking care that the proof works for small values of k, including k equals b. You want to clearly identify the conclusion of the inductive step, such as saying this completes the inductive step. And then finally, after completing the basic step and the inductive step, state that the conclusion, namely by mathematical induction, P of n is true for all integers n, with n is greater than or equal to b. So you can go back and review some of the examples that I quickly went over. I didn't go through the solutions / the proofs, but here is the rigorous approach that we're using in those cases. Okay, next let's talk about strong induction and well ordering. And so here is the material that we'll get into. We'll talk about strong induction. We'll have some examples of proofs, and I'll go over those quickly. It's not in the lecture notes, but you can refer to Rosen to get some more information about using strong induction in computational geometry. And then we'll talk about well ordering property. So in section 5.1, what we just went over, we introduced mathematical induction and we showed how to use it to prove a variety of theorems. In this section, we introduce another form of mathematical induction called strong induction, which can often be used when we cannot easily prove a result using mathematical induction. The basic step of proving by strong induction is the same as a proof by of the same result using mathematical induction. That is a strong induction proof that P of n is true for all positive integers n. The basic step shows that P of 1 is true. However, the inductive step in these two proof methods are different. In a proof by mathematical induction, the induction step shows that if the inductive hypothesis P of k is true, then P of k plus 1 is also true. In a proof by strong induction, the inductive step shows that if P of j is true for all positive integers, j not exceeding k, then P of k plus 1 is true. That is, for the inductive hypothesis, we assume that P of j is true for j equals 1, 2, 3, all the way up to k. The validity of both mathematical induction and strong induction follow from the well-ordered property, and you can see Rosen chapter appendix 1 for some more details about that. In fact, mathematical induction, strong induction, and well ordering are all equivalent principles, and this is shown in exercise 41, 42, and 43 if you want to go through that. That is, the validity of each can be proved from either of the other two. This means that a proof using one of these two principles can be rewritten as a proof using either of the other two principles. Just as is sometimes the case that it is much easier to see how to prove a result using strong induction rather than mathematical induction, is sometimes easier to use well-formed ordering than one of the other two forms of mathematical induction. So in this section, we will give some examples of how the well-ordering property can be used to prove the theorems. So that's just a rundown of what we're going to talk about. So for strong induction, this is what we have to prove P of n is true for all positive integers n, where P of n is a propositional function. We do the basic step, and then we do the inductive step, which we're seeing here. And so strong induction is sometimes called the second principle of mathematical induction or complete induction. And so that's a perspective that you can think about that. So here we come back to our ladder example. So using strong induction and the infinite ladder. Strong induction tells us that we can find all rungs if we can reach the first rung, and for every k, we can reach the first k, then we can reach k plus 1. So we have the basic step P of 1, and the inductive step, we assume that P of 1 all the way up to P sub k holds for an arbitrary integer k, and show that P of k plus 1 must also be whole. So this is a little bit different than mathematical induction, and we tried to go over that through words, but now we're getting a chance to see it for an example. So once again, I'm not going to walk through the solutions. So this is just now trying to prove this ladder example using strong induction, and you can see how that lays out here. So which one should we use? We can always use strong induction instead of mathematical induction, but there's no reason to use it if it is simpler to use mathematical induction. So in fact, the principle of mathematical induction, strong induction, and well-ordered properties are equivalent. We mentioned that, and these are the exercises you can refer to. Sometimes it is clear how to proceed using one of the three methods, but not the other two. So of course, you want to use the easiest way to help you figure it out. So then in terms of completion of the proof of the fundamental theorem of arithmetic, show that if n is an integer greater than 1, then n can be written as the product of the primes. I'm not going to go through this solution as I've done with all the things we've covered up to this point, but you can pause this and walk through this or go to Rosen. So here's an example of a proof using strong induction. Prove that every amount of postage of 12 cents or more can be formed using just 4 and 5 cent stamps. So we have the basic step and the inductive step. I'm not going to go through this, but you can see how that would work, and thus we can be proving that that is true. Well, what if we wanted to do it with mathematical induction? And so you can go back and forth between these two charts, between strong and mathematical induction, and you can choose and think about which one you think might be easier, at least for that example. Then the third thing that we mentioned, well-ordered property. Well-ordering property, every non-empty set of non-negative integers has at least an element. The well-ordered ordering property is one of the axioms of the positive integers, and that's included in Appendix 1. So see Rosen for that. The well-ordering property can be used directly in proofs, as the next example illustrates. So the well-ordered property can be generalized. So here's a definition. A set is well-ordered if every subset has at least an element. N is the order under less than or equal. The set of infinite strings over an alphabet using lexicographic ordering is well-ordered. So see Rosen some more for some more insight into that. In an example, I won't go through the solution. Use a well-ordering property to prove that the division algorithm, which states that if A is an integer and D is a positive integer, there are unique integers K and R with 0 less than or equal to R is less than D, such that A is equal to QR. I'm sorry, A is equal to DQ plus R. And here's a solution that you can revert to, and you can also go to exercise 37 to think about that further. Well, something I think that's interesting is now we get into recursive, and that will be the thing that I'm going to end as a high point when we finish up this chapter. So we'll talk about recursively defining functions, recursively define sets and structures, structural induction, and then finally generalized induction. So how do we go about doing a recursive definition? So a recursive function calls itself. A recursive or inductive definition of function consists of two steps. Specify the value of the function at 0, and then give a rule for finding its value at an integer from its value at smaller integers. We'll get a chance to see this shortly. Here are examples, and so you have the 0 case, but anything beyond that, it's related to its previous members, and so here's an example. Here's another example. So the n plus 1 is a combination of that value plus the previous one times together. And so thus we can see some recursive definitions that are laid out. Here's another example. I'm just going to skip over this. I think probably most, maybe all of you have heard of a Fibonacci sequence. And so you can be seeing how this plays out. And so the nth value is related to the previous two. And so thus you need to seed it with enough value to get started. And this is something that we'll come back to in chapter 8, but this is an example of what we've been seeing with these last few charts, but something that you might be familiar with. So here is an example show that whenever n is greater than 3, we can have a bound um, for a lower bound for that value. And so this is just some interesting mathematical formulas, closed forms that we could start to lay that out, which can be a useful thing for bounding the complexity before, so we can have at least a lower bound of where that would be. I'm just going to state this theorem, but I'm not going to go through it any more than that. So Lame's theorem. So let a and b be positive integers with a greater than or equal to b. Then the sum of the divisibles, the division used by the Euclidean algorithm to define GCD-AD, the greatest common denominator, is less than or equal to 5 times the number of the decimal digits in b. So a useful theorem, and we're just going to, like I said, skip over it for now. So this was the first result in computational complexity. And so we're getting a chance to get some insight into looking at things. And this was another area. And I'm not going to read the bio for Lane, but I'm sure if we did, you get a chance to get some context. And so please, I would recommend that you look over his bio and you'll get some better insight into what this is and why it's a useful thing to have. So let's get into recursively defining sets and structures. So it has two parts. The basic step is where we specify an initial collection of elements. And then the recursive step gives a rule for forming new elements in the set from those already known to be in the set. For example, we talked about the Fibonacci sequence. Sometimes a recursive definition has an exclusion rule, which specifies that the set contains nothing other than those elements specified in the basic step and generated by applications of the rules in the recursive steps. We will always assume that the exclusion rule holds, even if it's not explicitly mentioned. And we will later develop a form of induction called structural induction to prove results about recursively defining sets. So this is a computer science centric course, but although other folks in engineering and mathematics hopefully will find it interesting. And so how can we be proving the validity of algorithms that we codified in recursive language is something that we can be using. So here now we can just see some example of recursively defining sets and structures. I'm going to skip over this, but once again, you can pause the video and think about this a little bit further. We can do, so we have it for sets and structures. We can be doing it for strings, so alphabetical strings. Those are things that we can be doing as well. We can be doing string concatenation. So this can be something that you might be finding that you're doing. And so two strings can be combined via the operation of concatenation. So let sigma be the set of elements and sigma prime be the set of strings formed from the symbols in sigma. We can define the concatenation of two strings denoted by dot recursively as follows. And so you can just walk through that here and see what we're dealing with here, the syntax we're using, and the result of what we can be doing. W1, W2, abracadabra, coming from abra and cadabra. So we can determine the length of a string recursively. We give a recursive definition of L of W, the length of the string W. And so this is how we could be laying that out. And so we keep breaking it down to come up with that value. We can, in terms of balanced parentheses, we can give a recursive definition of the set of balanced parentheses. And so we can have algorithms to find if an expression is actually well formed. This can be something that would be used in the compiler, and you can be seeing like this works fine. This is not well formed. And so this would be the things that you would want to be doing, say, in a compiler or an interpreter to make sure that you capture stuff like that. You can also do an assessment of how well formed a formula is in propositional logic. And so the set of well-formed formula in propositional logic involving T, F, propositional, propositional variables and operators from the set. Here is a set. And so here we can be seeing how we can be looking at that with the basic set step and the recursive step. And so I'm just going to refer you to Rosen for more details, and just leave the existence that this is something that we can be doing. We can be analyzing propositional logic in this way. Okay, we'll have a couple charts that are looking at trees, and this gets into graph theory and some interesting things that we'll touch base in them a little bit later in the course. And so let's have some definitions. The set of rooted trees where a rooted tree consists of a set of vertices containing a distinguished vertex called the root, and edges connecting these vertices can be defined recursively. And so you have a single vertex, and then you start hooking things together. And this gives you a chance to start to walk through how that would work. And so building up a rooted tree, we start with the vertex. Then we can add one node and connect it, add another, a third, and a fourth. And so we can get that together. And then the step 3, then we can start to be adding one at a time to each of the next layer of nodes. And this is something that we'll get into in chapter 11. So this is building a rooted tree that you have this single top point and everything is built below that. And then we have another specialized tree called a full binary tree, and we'll come back to this. The set of full binary trees can be defined recursively by these steps. First, there is a full binary tree consists of a single vertex R, and so that here we can see that can be considered a full tree there. Recursive step of T1 and T2 are disjoint full binary trees. There is a full binary tree denoted by T1, T2, consisting of root R together with edges connecting the roots to each of the roots of the left subtree and the right subtree. So a binary tree, that it means that it only has 2 children, and thus we can see this. You can only have 2 children for each node. And so if we're going to start to build things out, this is what we do. And so this is a full binary tree that we end up with. Okay, here we have induction and recursively defining sets. And so I'm not going to go through this, but just as an example that we have here, show that the set S defined by specifying that 3 is an element of S, and that if X is an element of S and Y is an element of S, then X plus Y is in S, is a set of positive integers that are multiples of 3. And so here we have a couple different possible ways that we could go about proving this. And mathematical induction is the approach that we're showing. For structural induction, to prove a property of the elements of recursively defined elements, we use structural induction. So the 2 steps are: 1, basic steps show that the result holds for all elements specified in the basic step of the recursive definition. And then the recursive step to show that if the statement is true for each of the elements used to construct new elements in the recursive step of the definition, the result holds for these new values. The validity of structured induction can be shown to follow from the principle of mathematical induction. Okay, here are a couple other things: the height of a tree, the number of vertices, and so we can have a way of figuring those out. And so we're doing this recursively. So h of the tree, but then the subtrees in a binary tree only can have a maximum of 2. So it's going to be 1 plus this height of these lower ones. And then you're going to have to do that for T1 and T2 and keep moving down. And so once again, the number of vertices, we're going to have to be doing that recursively, and we get a chance to be seeing that laid out. And so here we have a theorem. If T is the height of the tree, then N, the number of the vertices, can be bounded by this value. So another example of something that can be useful for helping us to bound complexity. Then the last thing that we wanted to cover in this section is generalized induction. It's used to prove results about sets that are other than integers that have well-ordered properties, and we'll come back to this in chapter 9. For example, consider an ordering of an n by n ordered pairs of non-negative integers. Specify that x1, y1 is less than or equal to x2, y2 if either x1 is less than x2 or x1 is equal to x2 and that y1 is less than y2. This is called a lexicographical ordering. Strings are commonly ordered by lexicographical ordering, so having things in an ordered list has its benefits. And the next example, which I'll just show but not go through the solution, uses generalized induction to prove the result about the ordering pairs from n times n. So here we suppose that mn is defined by mn is an element of n times n, and we can have this laid out, and we're asked to be showing this relationship, and you can go ahead and pause the video to go through that in more detail or go and refer to Rosen. Okay, let's get into recursive algorithms. So we've talked about induction now, a couple of different types. Now we can be thinking about recursive algorithms. Now we get into some practical application. We can be proving that recursive algorithms are correct. We can get into recursion and iteration. These are two approaches. It's not in the presentation, but that's in Rosen you can look at, and then we'll spend some time, and I have a graphic that will give you a chance to visualize that, hopefully make it a little bit easier to grasp. So recursive algorithm, it's an algorithm that's called recursive if it solves a problem by reducing it to an instance of the same problem with a smaller input. For the algorithm to terminate, the instance of the problem must eventually be reduced to some initial case for which the solution is known. Okay, what I'm going to do for the next handful of charts is just to give you a perspective, and you can see the pseudocode here, and each example here, the function calls itself, and thus we see that it's recursive. So we have an algorithm for computing n. So if we start with n, then we call it again, and we do n minus 1 all the way down to when we reach the base case. So that's a recursive factorial algorithm. Doing exponentiation. So this is, we have power. And so what we do is we calculate the power at each level. And eventually we'll get to having an aggregation of A. So it would be however many times n is the number of times that we'll circle through this. A recursive greatest common denominator, a GCD algorithm. And so we can be walking through this. And so we keep calling GCD. We're using modular division to be figuring this out. So you can, we've covered this already, so you can look over that to remind yourself about GCD. What I'm just trying to do at this point is just, here's another example of an algorithm that's done recursively. We have the pseudocode, and with that, you could write it in whatever language you would like. And we have exponentiation. It's the same thing here. we're calling this M power. You can walk through this and see the textbook for further explanation of that, a little bit more complicated of an algorithm. Now we have a recursive binary search algorithm. And this is what we're going to get into binary search, and then we're going to get into merge search in a minute. So this is just a general recursive way of doing a binary search. And this is what that code, pseudocode would look like to perform that. See Rosen's for more details about that. Here is how we would prove the recursive algorithms are correct. So we've already talked about this so far. So here, this is for power. Prove that the algorithm for computing the powers of real numbers is correct. So this is now gets into some of the things we've talked about. And then we just have a handful of charts on an example of a sort. So we'll talk about sort and searching. But here is an example of a merge sort, which is trying to be a little bit more efficient than just a generalized sort. It works by iteratively splitting a list with an even number of elements into two subsets of equal length until the sublist has one element. Each sublist is represented by a balanced binary tree. At each step, a pair of sublists is successfully merged into a list with the elements in increasing order. Process ends when all sublists have been merged. The succession of merged lists is represented by a binary tree. Okay, well, here is what we see in Rosen. And what I did here was I just showed an example, but this also shows that you don't have to have just an even number. You can have an odd number of elements and it still can work. And so you work your way down this tree. This is how you're doing these sorting, and then you sort these elements gradually and then get to the result of everything put in a proper order. So I thought this might be a little bit easier to track rather than just this, but they're basically the same, although they're using different numbers, but you can be just letting this run a couple times and you can see that played out. So here is just an algorithm in the pseudocode for doing the merge sort. And so here we see that we're calling merge sort here. And so we have to put things in order, then we merge those things, and it definitely is something that would work well with a recursive approach. This is just some more details here that I would refer you to see Rosen to go over that. But you have to figure out two things. And so you want to be figuring out, put them in the proper order, and then you have to do the merging. And so these are the things that we're getting a chance to be laid out. And Rosen does a good job of looking at. In terms of the complexity, the big O complexity is n log n. So that's better than a brute force approach. There are some other examples that we'll be getting into, as well as into courses like data structures. We'll get into it a little bit more to have more efficient procedures for sorting, as well as searching. That'll come later, a little bit in this course, and also some follow-on courses. Okay, so that's it for this lecture. Thank you very much.